Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. We are with the last chapter of microwave engineering called as radar engineering. The radar, acronym for the radio detection and ranging, is to be addressed in the various details that we see in this particular chapter. After the introduction to the basic principles and the simple working, we have gone through the various topics so far, as like the block diagram completion, then the classification into the two basic types. We have also addressed the derivation with respect to the determination of the maximum range value for the pulse type of the radar. We have seen the block schematic, adding certain more details to the pulse type of the radars is also reported in the previous lecture there. Let us have this topic. So let us begin with. So here the topic is titled General Principles of Radar Receivers. In the previous lecture, we have gone through the detailed block diagram with respect to the pulse radar system operation here. Now, whenever the radar receiver, thereupon we have shown you the transmitter section that is having the modulators and the output tube, that is basically the microwave tube generating the microwave signal. The modulator, it was also there so that the pulse modulation over the carrier frequency signal that can be generated, and with the help of duplexer type of the transmitting antenna, it can be transmitted towards the intended target there. So after the reflection, it should be received by the receiver section. So for the receiver section, there are certain general principles that can be considered while design of this particular receivers. So let us discuss them. Now, the function of the radar receiver is for the detection of the reflected echoes there. So the echoes are to be detected in the presence of, we know there it is noise in the communication channel. There can also be the interference due to the another signals working onto the same frequency ranges, and there can be the clutter here. So if you have background of the communication engineering, you will be very well familiar with the noise and the interference term. But see what exactly the clutter is. The clutter is defined as any unwanted radar echo. So all the three parameters, noise, interference and the clutter, these are all unwanted signals with respect to the receiver operation here. So this is any unwanted radar echo that can be produced because of the reflections from the land, the sea, or it can be the rain, or it can be the birds, insects, the poles and the towers here. So these are the various objects into our surroundings, and this completes our nature here. So whatever the natural reflections come because of this particular one, but they are not wanted signals, so these are all accounted into the term clutter here, which is the unwanted thing here. So at the time of designing of the radar receivers, we have to consider all these three factors here. So now the designing aspect should be as such that whatever the signal is to be received, so that depends on to the transmitted signal also, that will compete with the noise, interference and the clutter parameters, and will be successful to be detected with the most possible efficiency value there. Now most possibly it is noted that for the radar receivers, the structure is of the super heterodyne receivers here. The purpose of using the super heterodyne receivers is that the super heterodyne receiver is having the good sensitivity. It also is having the high amount of gain value made possible by its particular structure. The selectivity and the reliability are also at the desired levels here. So therefore, the structure of the super heterodyne receiver that we have shown in the previous lecture in the block diagram at the bottom place is very important while designing of the receiver section for the radars there. So in the super heterodyne receiver, we have seen that we start with the low noise amplifier section. So basically we shall be having the term RF amplifier in general. This is the first block for the super heterodyne receiver here. For the RF amplifier, the task is to have the strength of the echo signal to be received with the raised values here. So echo signal strength is boosted up by the use of RF amplifier here. So while having the RF amplifier into the consideration, there it is the role of noise figure that we can be denoting by capital F here. So the good value of the noise figure or the noise factor can be achieved if we can have more complex circuitry associated with the RF amplifier here. The use of parametric amplifier or the traveling wave tube can also be there for the RF amplifier here, but when we use the TWT type of the RF amplifier, it has the feature that the higher order values have the saturation. So this point can be shown with the help of one schematic diagram. So here we see the schematic diagram has plotted the input power of the traveling wave tube versus the output power of the traveling wave tube, and the nature of the relationship can be seen in this particular curvature. So initially, with the increase into the input power of traveling wave tube, the amount of output power was increasing with great values, so we can say that the gain factor that it was at the high values there. Afterwards, at this particular band, it has reached to the saturation level. So though the input powers are increasing a lot, we have lowered down into the increase of the output power of the TWTs here. So this way, because of the saturation, the use of TWT into the RF amplifier can be working as a limiter for the controlled operation here. Now next to the RF amplifier, the very important block is the mixer here. So the mixer is also having the integrated part that it is the local oscillator. Now most possibly into the super heterodyne type of the receiver for the radars, here we make the use of crystal mixers here. So for the crystal mixers, the schematic representation with the help of the local oscillator can be shown like this. So from the RF amplifier, whatever the signal we obtain, the frequency represented as F suffix RF is the one input, and F suffix LO from the local oscillator, the known value of frequency, is the second input here. Now the work of the mixer is to have the production of the IF, intermediate frequency. So it is the difference of the two known local oscillator frequency minus the RF frequency here. So basically the work of the crystal mixer is to have the conversion of RF energy into the IF energy with minimum possible losses and without the spurious responses, I can say. Now the use of silicon type of point contacts Also, the use of Schottky barrier diode as discussed in the previous lecture, and the crystal diodes is there for the crystal type of the mixers. Now you can see here, along with the mixer, the local oscillator is the integrated block here. So while designing the receiver section of the radar, there it should be also the care should be taken that the local oscillator will not be adding certain kind of noise to the signal there. So though the local oscillator frequency is the known one, it should be completely noise free here. So because to have the removal of the local oscillator noise, practically there should be certain techniques to be opted there. So one of the technique to have the removal of local oscillator noise is to make the use of balanced mixer with the help of match hybrid junction T here. So in this particular schematic diagram, you can see a balanced mixer here. So in the balanced mixer, we have the first input from the RF amplifier here, whereas the second input is from the local oscillator here. So these are basically fed as inputs to the junction arms of the magic T hybrid T here. So these are the pair of collinear arms, and these are the pair of E arm and H arm here. So H arm exhibits the property of H plane T, whereas E arm exhibits the property of E plane T here. So here we have the outputs at the local oscillator and the RF both increased and in phase, whereas they have the reversal of the phase at this particular collinear arm. Next to that, we have the crystal diodes connected here, D1 and D2, with the values noted here, EI, EO, EI dash, EO dash for the second branch here, and here they have been connected to the subtractor so that the cancellation will result into the noise is equal to 0 and only the IF output into the pure form without the noise can be obtained here. So for the magic T, the details can be given into the one more schematic diagram. So here in the schematic diagram, there have been shown the mount of the crystal diode covers here. So 2 onto the port number 1 and 2 onto the port number 2. So this will be resulting into the IF outputs also. So this is going to the second branch, this is going to the first branch, which are fed as input to the subtractors that we have seen in the previous schematic diagram. So in this super heterodyne receiver, there it is another block that it is called as IF amplifier, which is a block in between the mixer and the detector here. Now the work of the IF amplifier is to have the adequate amount of the image frequency to be suppressed here, so that the IF amplifier is made a broadband to permit the use of fairly narrow band pulses here. So in this schematic diagram, you can see for the broadband use of the amplifier, we have the frequency values plotted onto the horizontal axis, whereas the amplitude levels can be shown onto the vertical axis here, and here it is the pulse having this much of bandwidth here. So the center frequency is represented as the IF frequency, and this is the representation for the IF amplifier block here. Now after we have the last block to be the detector here, the use of antenna to work for the transmitter and now here for the receiver is very important. The antenna should be into the duplexer mode here. So the duplexer mode employs here the fast acting RF switches here. The fast acting RF switches or the gas discharge. The gas discharging tubes are basically there, that those are called as capital TR for the transmit and receive here. The TR can also be regarded as basically switch here, and along with the TR there it is also the possibility of having ATR. ATR standing for the anti transmit receive switch here. So as we know that the duplexer has the responsibility to take the same antenna to be used for transmission as well as for reception. So focusing on to the reception switching here, the fast action should be taken to get that particular switched here. So these are the two types of the switches, TR and ATR here. So with the help of the gas discharge tubes also it is all possible. So this is the schematic diagram of a typical TR tube here, the transmit receive switch here. In this particular schematic diagram, a resonant cavity is associated with a special cold cathode tube here. So here we can notice the coupling loop for the connections to be made here. With the help of the coaxial inputs we can provide from this particular end, whereas the coaxial type of the output can be taken out from the latter end. The same type of the coupling loop here we are provided here. Now inside there it is the resonant cavity, the resonant chamber it is mentioned there, and here it is the gap corresponding to the TR tube which has the inert gas at the low pressure, for example the neon or the helium filled up in this particular device here. Now the simple duplexer and the connection with respect to that of the TR transmit receive switch just now we have seen. The more advanced type of the duplexer is also said to be the branch type duplexer here. And for the branch type duplexer, the operation can be explained with the help of the schematic diagram, where the connections with respect to the transmitter and that of the receiver are made possible by use of the TR switch and the ATR switch, which gets the connections into the alternate fashion here. So here we see the transmitter section and the receiver section. The line length corresponding to the main waveguide towards the antenna from the transmitter section is having the lambda by 4 at the nodes X and Y. This line length can be denoted for the ATR switch, where it is the same length for W to Z points for the TR switch which is connected to the receiver here. Whereas both the connections corresponding to the ATR switch and TR switch are separated by the same kind of the distance denoted lambda by 4. So it is quarter to the guide wavelength. So lambda in general can be regarded as the guide wavelength here. So these were the various general principles to be considered while the design of the receiver for the radar system is to be there. By the next lecture, we shall add some more information with respect to the modulators being used in the radar systems. So for more such details to enhance your knowledge for microwave engineering topics, you can subscribe to Ekeeda channel. Thank you.